a mini course on CMB. I mean, of course, it's a must. So Emmanuel Schaan did his PhD in Princeton, so he's European, but he did basically all of his career in the US, then moved to Berkeley for a postdoc, and then he landed at SLAC, where basically which left yesterday to come here.
Yes.
So all what you know about CMB, you should be knowing by Friday if you follow Emmanuel's lectures.
Great.
Thank you.
Thank you so much. Thanks a lot for the introduction, and thank you very much for having me. It's a real honor and a pleasure to be able to tell you about the cosmic microwave background over the 5 courses of this week. The CMB is one of my favorite topics, perhaps in all of physics. And so I'll try to convey some of that excitement, and I hope I'll do justice to it, and by the end you'll be as excited as I am about the CMB. I will be using slides a lot for these lectures, and so please feel free to take notes as you want and can, and those slides I'm sure will be made available to everybody. I also wanted to say, please don't hesitate to raise your hand and ask questions. And let me know if what I'm saying makes sense or if it's completely confusing. So without further ado, thanks a lot for being here, and let's get started talking about the cosmic microwave background. And I thought I would start with some motivation about why one might want to learn about the cosmic microwave background. And so this is my biased list of motivations from someone who loves the CMB. And so the cosmic microwave background, as hopefully I'll be able to convey, is really an incredible astrophysical object, a really unique one. And I feel like we're really, really lucky that there is a cosmic microwave background out there to tell you a lot of things that we know about the history of the universe. And so it is the oldest light that we can see in the universe. And so it tells us a lot about the initial conditions of the universe. It is perhaps the most perfect black body spectrum in the universe. You might want to fact check this. But a fun fact is that the measurement of the spectrum of the CMB that we currently have is more accurate than we have ever tested the Planck function to describe what a black body is. It is one of the simplest astrophysical observables in all of astrophysics. Gaussian field, linear sound waves in a plasma. It'd be really difficult to ask for anything simpler. Stir a cup of coffee and the physics in there is a lot more complicated than that of the cosmic microwave background. And despite being so simple, it has an incredibly rich phenomenology. And so that's what I'll be telling you about in the next few lectures. And so there's a lot going on, a lot of simple physics, but very rich physics going on that can tell us a lot of different things. It is perhaps the or one of the most powerful single probes of cosmology. There's a lot you can learn from just looking at the cosmic microwave background. And really, it fits within this picture that I really like of using the observable universe as a fundamental physics lab. And so, of course, in many respects, the universe is the most terrible fundamental physics lab you could imagine because you don't get to turn the knobs and rerun the experiments. But there's one respect in which it is the very best fundamental physics lab, and that's when it comes to gravity. And so by looking at the CMB, you can derive key evidence for this hot Big Bang model. You get to look at the baby universe. It's one of the cleanest probes of the initial conditions of the universe. You can determine almost all cosmological parameters and learn about the age of the universe, its composition, how it evolved to today. You get to probe a very high energy physics, much higher energy than the temperature of the CMB when it was emitted. You can test whether gravity is well described by general relativity. You can learn about particles beyond the standard models. So neutrinos, which are in the standard models, but their masses, which is not, as well as the existence of additional weakly interacting particles. And finally, the CMB doesn't just tell you about the initial conditions of the universe, because the CMB photons, in order to reach you, have had to travel across the whole universe. And as a result, the CMB also tells you about late times and the large-scale structure of the universe. So a lot of things you can learn from the CMB. And why should you learn about the CMB now? It's been around for 14 billion years, so why the hurry to learn about it now? From a US perspective, this has been ranked the highest priority for all of particle physics in the US, was an experiment to build the cosmic microwave background. And this was also ranked one of the highest priorities in the National Science Foundation in the US for astrophysics. So both astrophysicists and particle physicists are excited about this cosmic microwave background. Yes, unfortunately. But still a lot going on, and I'll talk about this in my last lecture in terms of new experiments. And so before jumping into more of the actual physics, I thought I would start with some useful references. The cosmic microwave background, the primary anisotropes, the one from the early universe, were basically figured out a few decades ago. And there's a lot of really good references on the CMB. So personally, I love Wayne Hu's tutorials on his websites. A lot of cool animations, images, and ways to visualize what's going on. So really, perhaps the first resource you should go to. A lot of good review papers. So this Hu and Doddleson 2002 contains a lot of what I'm going to be telling you over the course of a week in only something like 7 pages. So it's a bit concise, but all the phenomenology is in there. And then if you want to dig into actual derivations for all of this, I would recommend this Hu and Sugiyama 1996. And for CMB polarization, which will be the topic of the third lecture, this paper is a really great resource. And finally, there's a lot of textbooks and lecture notes. Some of them are available online as PDFs, other you may have to purchase. I personally really have liked the cosmology textbook of Daniel Baumann, having learned a lot of my cosmology from the lecture notes of Anthony Challinor at Cambridge, which I think a lot of them turned into those textbooks. Yes, question? Mm-hmm. Oh, why is that? Yeah, so hopefully we'll learn a bit about this throughout the course of the lectures. But in terms of particle physics, this is because of the new particle physics beyond the new particles beyond the standard model that we might be able to learn about, as well as learning about this inflation, which you all learned about last week. So properties of inflation, masses of the neutrino. So a lot of particle physics you can do really with the universe as a lab. And for astrophysics, it's sort of the second part, the part where the photons travel throughout the universe and interact with late-time objects. This imprints shadows onto the CMB that tell you a lot about astrophysics, a lot of things about galaxies you couldn't see by just looking at the galaxies in visible light. So particle physics and astrophysics in that CMB, yeah. Thanks for the question. So these are all of the resources I wanted to mention. Of course, there's a lot more, and so apologies for not representing some that you might like. In terms of outline for these lectures, the first lecture today will be a gentle introduction about what is the cosmic microwave background and what you should know about the monopole, by which I mean not the fluctuations in the cosmic microwave background. Tomorrow will be temperature fluctuations. I think this is probably the most beautiful physics in the cosmic microwave background, and I got really excited preparing these lectures, so there's probably too much, so I might have to just stop myself, but really excited for tomorrow. Polarization is very cool, tells us a lot about inflation. Lecture 4 is actually the topic of my research, which is how to use the cosmic microwave background to probe late times and their large-scale structure. So really excited about this. And depending on how much time I have, I hope to spend quite a bit of time on how one actually measures the CMB and what the ongoing and upcoming experiments you should be looking out for. So I don't know if there's any question before we get started with today's lecture. Yes? Mm-hmm. That's right, yeah, and we'll talk a lot more about this. Right, and the question was, how do we see those secondary anisotropes that tell us about the large-scale structure? Do we learn about them by looking at the CMB on small scales? And I think to a large extent, that's the case. Yeah, looking at the CMB on the smaller scales lets you probe those secondary anisotropes. And that's sort of why the observational frontier for the CMB right now are temperature on small scales and sort of polarization on both large and small scales. Thank you. All right, so what is the CMB? What should we learn about the temperature monopole? My goal is that after this lecture, you should be able to explain what the cosmic microwave background is to anyone in the street, to your friends and your family, in a few sentences that hopefully they'll understand. And you'll be able to tell them why it's strong evidence for the hot Big Bang model and what that means. I want you to remember after this lecture about the black body spectrum of the CMB, why that's important, the temperature of the CMB and what that tells us, and sort of the typical numbers for this CMB. I want you to take away Thomson versus Rayleigh scattering, as well as key steps in the universe's thermal history, especially recombination. So let's jump into it. And to ease us into the topic, I thought I would start with a lot of visualizations and then a bit of formalism towards the end. So as you know, and you've learned about last week and this morning, the universe is expanding, by which very schematically you could say that galaxies are moving away from each other. And so if the universe is expanding when you move forward in time, it means that when you move backwards in time, the universe used to be smaller than it is today. And that's what we mean by the hot Big Bang model. I'm not talking about a hypothetical singularity where everything would be at one point. I'm really just talking, when I say hot Big Bang, about the fact that the universe used to be a lot smaller. I'm basically just talking about the expansion of the universe. And so going back in time, the universe had to be smaller, and when you compress things, you know, you make them denser. When you compress things, you tend to make them hotter. So hot Big Bang, the early universe was more compressed, denser, and therefore hotter. The second physics fact you need to know to understand the cosmic microwave background is that everything that is hot glows. And so in particular, we all glow, all of us in this room. We just glow in infrared light that our eyes cannot see. But if we were a bit hotter, like a piece of metal in a furnace, we could start to glow in the visible, in the red. And if you keep heating it up a bit more, you will start to glow yellow or white, just like incandescent light bulbs or the sun at about a few thousand degrees Celsius or Kelvin. And so these are very simple arguments. You know, we have seen the universe expand. Therefore, we can predict that the early universe was denser, therefore hotter, and we know that anything that's hot glows. Therefore, we expect the early universe to glow. And so this sort of very simple theory prediction is that you should see today the leftover heat or the afterglow or this relic light from the hot Big Bang. And this is what we call the cosmic microwave background. Cosmic because it comes from outer space, the cosmos, not even our Milky Way galaxy. Microwave because it turns out this is the range of wavelength or frequencies at which we observe it today. And background because it should fill all of space, because this light came from everywhere in space. And because it is sort of the oldest light we can see, it is behind everything, hence background. Now, this cosmic microwave background was predicted and discovered more or less in the same journal issue, where engineers at Bell Labs were studying the properties of telecommunications at microwave frequencies and finding this really annoying source of noise that they couldn't get rid of. And in the same papers, a crew of physicists, including Jim Peebles, made the prediction that this cosmic microwave background, this fireball from the hot Big Bang, should be basically at the same frequencies. And so this is the discovery of the cosmic microwave background in 1965, and so already quite a long time ago. And if you look at it, if you make a map of it at every position in the sky, and you put this map of the sky into a planar projection like this, what you might see is something like this. So this is meant to be a uniform color all over the sky. And we see it today at only 3 degrees above absolute zero. But as I'll tell you in a moment, we know that when it was emitted, it was more like 3,000 Kelvin or 3,000 Celsius. And so if you ask, what does light at 3,000 Celsius look like? If you think about it, the sun's surface is about 5,000 or 6,000 Celsius. And so this is about half that temperature. It would look something like this. So if you had been around back then when the universe was at 3,000 Celsius, it would have looked this color in all directions everywhere. A fairly hot and unpleasant place to be. But this is what the baby universe looks like. So when you look at this baby universe, what you see is this picture. It's very warm and cozy at 3,000 Celsius. These are the initial state of the universe. Before we talk about anything related to do with potential variations in temperature from point to point, there's a lot you can learn from just the sky average CMB intensity. And as always, when you're studying light, the first thing you can do is to decompose it into its constituent wavelengths and measure a spectrum of it. And so this was done extremely well by the COBE satellite. And what you can see here is the light intensity as a function of frequency. The points you see here are measurements from the satellites where the error bars have been multiplied by 400 so that you can see them on this plot. And the theory curve is the Planck function for blackbody. And so what you can see is, again, a remarkable blackbody. And this is what I was trying to tell you by saying it is perhaps one of the most perfect blackbodies in the universe. So an excellent blackbody. And the way this measurement was done was differentially. It's often really hard to make absolute measurements of things in physics in general because it means you need to calibrate your instrument and have it remain stable to very high precision. It is often much easier to make a differential measurement where you might have an onboard blackbody on your satellites and you compare the light from this blackbody to the light you see in the sky. And what this measurement showed actually is that the light in the sky matched what you expect from the blackbody to a higher precision than we have tested the Planck function to match a blackbody. So an excellent blackbody. And why do we care about that? Why does that matter? The reason it matters is because the blackbody is the spectrum of thermal equilibrium for photon gas. And so what it means is that when the CMB was emitted, the universe was basically in thermal equilibrium. And so that's a crucial bit of input. A question, yes? Yes, you definitely want that blackbody to be an extremely good one. And then the question is, how do you test this? And that's a really good question, and I think a really hard one, actually. And it's a question that people are revisiting now as they're thinking about spectral distortions of the CMB. And so I've told you that the CMB is an excellent blackbody, to very good approximation. But we might talk in the last lecture about the fact that there are distortions we expect away from the blackbody in the CMB, and those are just very, very, very small. And so a number of experiments have been proposed to refine this measurement and shrink these error bars a lot further in order to try to detect some of those spectral distortions. And yeah, I think experimentally it's a really hard problem. Thanks. And so, right, so you have this picture of thermal equilibrium. The early universe was in thermal equilibrium. And the CMB that we see is a clear theoretical prediction from the hot Big Bang model. And when people ask me, friends or people in the street, how is the CMB evidence for the hot Big Bang model? A short answer I can give without explaining all of this is if you've ever sat in a bus or in a metro, there's this empty seat, and you take it and you sit down and you feel this unpleasant heat under you, you know that somebody was sitting there before you. And that's sort of what the CMB is. The CMB is this leftover heat, this afterglow that tells you that something warm was there before. And so in this way, the CMB is evidence for the hot Big Bang model. Maybe I'll pause there and remind you of this. What I mean by this is something I would like you to just remember by heart and be able to explain to anyone. So we know that the universe is expanding. And what this implies is that going back in time, the universe was a lot denser. When you compress things, they get hotter. And so the early universe had to be hotter. And this is what we mean by the hot Big Bang model. Not necessarily the existence of a hypothetical time zero or singularity, just the fact that there's this expansion, and therefore the early universe was hotter. And since anything that's hot glows, we would expect the hot early universe to glow. And indeed, we do see this leftover heat, this afterglow from the hot Big Bang, and this is what we call the cosmic microwave background. It is one of our strong evidences for the hot Big Bang model. And its spectrum tells us that the early universe was in thermal equilibrium. So I don't know if there's questions at this stage before I move on. Okay, so then a few just very quick resources. These are very short YouTube videos, 10, 15 minutes. Things like you can watch at home while doing your chores, like doing the dishes, which is not interesting. You can listen to those. These explain basically just what I went over, again with intuition and very little formalism. So in case they're useful, I just wanted to bring them up. So now, now that we know about this cosmic microwave background, just to put it together in perspective, starting from here on Earth around the sun and zooming out to the edges of the observable universe, we have this picture of what the observable universe looks like. And so here we are around the sun, our star. If you travel outwards, you find that the sun is only one out of many, many stars in the Milky Way, our own galaxy. So this number of about 100 billion, or 10 to the 11 stars, typical number of stars in a galaxy. And if you keep zooming out, you'll find more galaxies. In fact, many, many, many more galaxies. We estimate that in the observable universe, what we're able to see around us, of course, this observable universe has an edge because the universe is only 14 billion years old, and so light could only travel so far. So we estimate that in this observable universe, there's about 100 billion galaxies, each of which with typically 100 billion stars. And finally, as you continue zooming out, you start to see sort of the, in practice, edge of the observable universe, which is this cosmic microwave background, 40 billion light years away. So this is sort of our observable universe. Online, you might be able to find these beach balls of the cosmic microwave background. If you hold it in your hand, you have the whole observable universe from our perspective in it. And as you zoom in, galaxies, finally us, and the sun. So, okay. To continue on perspective, there's a few more sort of background things I wanted to say about the cosmic microwave background and where it sits compared to other observables of the universe. And so what you see here is a timeline of the history of the universe with a hot Big Bang on the left and us 14 billion years later all the way here. The cosmic microwave background, as I'll tell you in a moment, was emitted soon after the Big Bang, only 400,000 years. Only because 400,000 is a small number compared to 14 billion. Closer to us today, there are many, many probes of the large-scale structure of the universe, which David is going to tell us all about. And these includes galaxy surveys. And so a lot of the game in cosmology is that you get to observe the statistics of the initial conditions of the universe by looking at the cosmic microwave background. And you get to observe the statistics of the final conditions of the universe using large-scale structure observables. And if you're able to match the statistics of the initial and final conditions, if you're able to find a model that makes the initial conditions evolve into the final conditions, you may have a good model for 14 billion years of evolution under gravity. And so you may have a good model for the composition of the universe and for how gravity works inside of it. So I've mentioned the CMB and large-scale structure observables. I also wanted to highlight another probe of the universe, which is somewhat new, and it's called intensity mapping. And intensity mapping is about observing the cosmic microwave background, observing galaxies in the same way that we observe the cosmic microwave background by making blurry, pixelated maps of them. And those hold the promise of perhaps observing those 80% of the volume of the observable universe that are currently uncharted. So I won't say more about line intensity mapping. I just wanted you to have sort of a global view of a bunch of cosmological probes. So that's all I wanted to say about this. And for the rest of the lecture, my plan is to move on to tell you a bit more detail and a bit more formalism about the universe's history, its thermal history, and specifically the part that's relevant for the cosmic microwave background. So I don't know if before I do this, if there's any questions or thoughts from anyone? Right. So the question was, when we talk about intensity mapping, where is this intensity coming from? Who's emitting that light? And so in the case of those light intensity mapping experiments, the light typically comes from individual galaxies. And so these may be line emissions from galaxies. And the reason why you like line emissions is because they have a very well-defined frequency or wavelength. And therefore, if you can easily map the observed frequency or wavelength to the actual redshift of the source. So right, the light intensity is coming from the line emission of these galaxies. And the philosophy of those light intensity mapping observables is that often for cosmology, you're trying to measure the density fluctuations on very large scales. Typically, the baryonic acoustic oscillations are order 150 megaparsec. And so why would you spend your time resolving every single galaxy when you only care about the large scales? So the idea of light intensity mapping is put some big pixels on the sky where you may have many, many galaxies, and you don't try to resolve the galaxies, but you will still get an idea of the large-scale fluctuations in the matter density field. Thank you for the question. All right, so moving on to the universe's thermal history. Earlier, I've told you that the early universe was hot, and hot things glow, and therefore we should see this light from the Big Bang, the cosmic microwave background. This is not incorrect, but perhaps it was a bit vague. And so let's be a bit more precise about what we are seeing, when we look at the cosmic microwave background. So in this table here are listed a few of the key steps in the thermal history of the universe as is relevant for the cosmic microwave background. So you probably remember from last week that the early universe was radiation dominated, meaning the energy density in the universe was mostly in the form of radiation, light and neutrinos. And because the radiation energy density dilutes with the expansion faster than the matter energy density, at some point, the matter comes to dominate the energy budget of the universe. And so this epoch of equality between the energy density in radiation and matter occurred at about redshift of 3,400, or about 50,000 years after the Big Bang. This transition will play an important role tomorrow when we talk about the physics of the fluctuations in the CMB temperature, but I just wanted to mention it right now. And then the key milestone in the history of the universe for what concerns the cosmic microwave background is this recombination epoch. And this is a dramatic phase transition in the history of the universe that occurred at redshift about 1,000 or 250,000 years after the Big Bang. And so what recombination is illustrated in this drawing here. So when you take a gas and for example, the gas in this room, and you warm it up, once the temperature gets hot enough, you'll find that you break the molecules in the gas into atoms. And if you keep compressing it and keep warming it up, you'll find that the atoms will break into nuclei and electrons. And so in the universe, the most abundant element is hydrogen. And so for the most part, in this lecture, we'll only be talking about hydrogen. And if you break a hydrogen atom into a nucleus and its electrons, you end up with protons and electrons. And so at some point, the early universe was hot enough to be this ionized plasma with free electrons and free protons zooming around. In this plasma, the electrons and the protons collide and interact via Coulomb scattering, meaning just the electrostatic force. And in this plasma, where you also have light and therefore photons, the light can also bounce around. It can bounce on top of the electrons or the protons via a scattering process that's called Compton scattering, or in its non-relativistic limit, Thomson scattering. So when we talk about the CMB, you'll hear a lot about Thomson scattering. It's a very efficient, very high cross-section scattering between photons and electrons and protons. And more specifically, the relevant scattering here is mostly with electrons. And that's because Thomson scattering, the cross-section, the effectiveness of the scattering depends on the mass of the object on which you scatter. And the lighter you are, the more the scattering is efficient. And as you know, electrons are about 2,000 times lighter than the protons. So when you think about this hot, dense universe, you think about this ionized plasma. You have protons, you have electrons, you have photons. And these are very well coupled together because between electrons and protons, you have this Coulomb scattering, which is very effective. And between photons and electrons, you have this Compton or Thomson scattering that's also very effective. So basically, you can think of this plasma as tightly coupled, meaning if I compress a little location of it and I have more protons, I'm also going to have more electrons and more photons because they're tied together by this very effective scattering. But as the universe expands and cools, at some point, and we'll talk about exactly when that happens, at some point, the electrons and the protons will recombine and form hydrogen atoms. And the reason they do is because energetically, an electron and a proton prefer to be bound together. It's a state with lower energy. How much lower? Lower by what we call the ionization energy of neutral hydrogen. And so as the universe evolves and the temperature drops, eventually the electrons get captured by the protons and form neutral hydrogen atoms. And when that happens, the story changes dramatically. So of course, the electrons are still very tightly coupled to the protons because they're even more so coupled. But now the photons are no longer interacting with charged particles as they were before. They're interacting with hydrogen atoms, which are neutral. And the scattering that occurs here is what we call Rayleigh scattering. It's the same kind of scattering that's making the sky blue and the sunset orange. And that scattering is just a lot less effective. And so once the electrons and protons recombine into hydrogen atoms, the typical mean free path for this photon becomes a lot larger. The photons are no longer tightly coupled to the hydrogen gas, and they start to travel away. And roughly speaking, the reason this matters for the cosmic microwave background is that when photons are tightly coupled to the baryons, by which cosmologists refer to electrons and protons, the universe is basically opaque. So the mean free path for this photon is very small compared to the size of the universe, the Hubble scale. Whereas once recombination occurs, with this Rayleigh scattering, the mean free path becomes comparable and larger than the size of the universe. And so the universe all of a sudden becomes transparent. So this is really a key phase transition in the history of the universe. Yes?
The cross-section is smaller, like
Mm-hmm. Yeah, so yeah, indeed, the question was, is the Rayleigh cross-section between photons and hydrogen atoms smaller than between photons, Thomson scattering off of electrons? And yeah, that's the crucial bit of information. It is why, after this phase transition, the universe goes from opaque to transparent. And so this is, roughly speaking, when the CMB is emitted. And so it is very hard to see earlier than the CMB because the universe was opaque. And at that transition, the CMB is emitted. And so when we look at the CMB, we see exactly that moment when the photons decouple from the baryons. So now on this table, you might notice that there's different entries for recombination, photon decoupling, last scattering, baryon decoupling, and they all happen sort of in the same range of redshift, but not exactly the same redshift. So what do we mean exactly by this? This is what I'm going to explain. And I'll start with describing how this transition occurs and when. And so we've talked about thermal equilibrium in the early universe. And so the simplest model you may have, question, yes? Right. Yes, that's a really good question. So the question is about polarization of those photons and polarization of the cosmic microwave background. Yeah, polarization is a big topic, so that'll be the subject of our lecture 3. So I'll tell you a lot more about this then. But in short, yes, the polarization that we see in the cosmic microwave background is the result of this Thomson or Compton scattering in specific configurations. If you scatter, if you take an electron and you shoot photons at it from all possible directions, if the light from all directions has the same intensity, you will end up with unpolarized light. But if that's not the case, you can generate polarization. And so we'll talk a lot more about this. Thank you. So we'd like to describe how this recombination transition occurs, what's the physics of it, and how does it happen. And so the first idea you may have, the first approach is, since we have this picture of thermal equilibrium in the early universe, the first idea you may have is, if you tell me what the temperature is in that universe, and you tell me how many baryons there are, how many photons there are, I could try to compute what's the equilibrium state. And so for any given temperature, what is the equilibrium abundance of neutral hydrogen versus ionized hydrogen? And then what we could do is we could let the temperature go down as the universe expands and see how those fractions change. So I'm probably going to leave as an exercise to you later to derive these equations, the so-called Saha equations that I'm going to show you. But I'll give you the qualitative steps for how you derive it. And so the chemical reaction you want to consider is the following, where you have an electron and a proton. These can recombine to form a hydrogen atom and to emit a photon. Or if you have a hydrogen atom and a photon that hits it, if the photon is energetic enough, the photon can break apart this hydrogen atom into an electron and a proton. And when you have a chemical reaction, there's a way to know what the equilibrium abundances are going to be. So in chemistry, you run your reaction. The reaction often can go both ways. And you can ask, what am I going to end up with at the end? And in thermodynamics, the way you typically derive this end result is by equating the chemical potentials. The equilibrium is the state in which if I were to take one hydrogen atom and break it, or if I were to take an electron and a proton and combine it, I would not change the energy of the system because I'm at the minimum of this thermodynamic potential. And so when you write what this means, to be at the minimum of the energy, and to have those chemical potentials equal, you end up with this equation. And so let me tell you what the letters mean in there. So Xe is what we call the ionization fraction, and it's the ratio of free electrons over protons plus hydrogen atoms. And so if all of your matter is in the form of neutral hydrogen atoms, Ne is 0 and your ionization fraction is 0. And if all of your hydrogen atoms are ionized, they're all broken up, well then NH is 0, and you have as many free electrons as free protons, so that the ionization fraction is 1. So the ionization fraction here is a dimensionless number between 0 and 1. In the early universe, when the universe is fully ionized, this ionization fraction is equal to 1. And as the phase transition occurs and all the ions combine into hydrogen atoms, that ionization fraction drops to 0. So to track the progression of this recombination, phase transition, what we need is to basically just make a plot of the ionization fraction as a function of time, or equivalently as a function of the temperature of the universe. Okay, so that's the ionization fraction. And one factor you may have expected to be present is this one. So what does this mean? What determines whether a photon can break a hydrogen atom into a proton and an electron is the photon has to have enough energy to unbind the atom. And enough energy means the photon has to have more energy than it takes to break a hydrogen atom. That energy is called the ionization energy. and you can measure it by comparing the rest masses of the two states, the ionized one versus the bound one. And so that energy is 13.6 electron volts. So that number clearly should play an important role. And whether or not there are photons with enough energy to have more than this energy is a statement about the temperature of your gas. And so naively, you know, if I have a gas at equilibrium at a certain temperature, what fraction of my photons will have energy higher than, say, EI? It'll be this Boltzmann factor, exponential of minus the energy you care about divided by KT. And so naively, you know, the key energy scale you have in your problem, since we're talking about recombination of hydrogen, is how much energy does it take? What's the energy difference between a broken up hydrogen or recombined hydrogen? And so naively, you might expect that recombination should therefore occur when the temperature, KT, is of order this energy in electron volts. So that would be the naive guess. And I don't know if you have a quick conversion in your head for how to convert, for example, electron volts to temperature in Kelvin. I don't know if anyone knows roughly what 13 eV would be in Kelvin. And maybe an easier question, 1 eV, how many Kelvin typically? So a quick conversion that I like to keep in my head is 1 eV about 10 to the 4 Kelvin. So 1 eV, 10 to the 4 Kelvin. This is just a number I remember. And it's a helpful number because if you want to do particle physics with the CMB, particle masses are often in eV, but the temperature of the universe is often in Kelvin. And so it's useful to be able to make that conversion. And so naively, I would expect recombination to occur at, say, 10 eV, so something like 10 to the 5 Kelvin. And if you look at the table I showed you, the temperature for recombination that's quoted is not 10 eV, but less than 1 eV. And it's not 10 to the 5 Kelvin, but more like 10 to the 3. So what's wrong with the simple intuition I gave you? And the answer is that the formula is not just this term. There are other terms in the formula. So, okay, there's one that compares the temperature of the universe to the mass of the electron. And so that term matters a bit, but it turns out not that much because here you have an exponential that varies very fast, and here you have a power law in temperature. So I can sort of forget about it. But there's one very important term here, which is this quantity eta, which is what we call the photon to baryon ratio. So how many photons in the universe per baryon do I have? And this number turns out to be extremely large, 10 to the 9. And so in the universe, you have a lot more photons than you have baryons. And because of this, because you have so many photons per baryons, even if the fraction of photons that have enough energy, that fraction is very, very small, because you have 1 billion photons for each proton, you only really need order 1 of them to be around to break that atom. So even though that exponential here is small, most of my photons don't have anywhere near the energy to break up a hydrogen atom. Because I have so many photons, some of them will have some outliers in the tail that have enough energy. And so qualitatively, this is what the Saha equation tells us. It tells us that clearly the ionization energy of hydrogen matters, but another crucial parameter is this very large photon to baryon ratio. And so you can actually just plot this, you know. Here you have an equation for the ionization fraction as a function of temperature. And so, you know, you can express Xe equals function of temperature. And if you do, you'll get something like this. So Xe as a function of temperature. So confusingly on this plot, early times are on the right, high redshifts, low high temperatures. And time goes on in this direction towards lower redshift and lower temperatures. And so what you can see is, in fact, if you just plot this equation here, you will get this curve where at early times the ionization fraction is 1, the universe is entirely ionized. But as the temperature drops, the universe becomes entirely neutral. And this occurs at redshift of about 1,000 at temperatures of about 0.3 eV. So again, 0.3 eV, you know, if 1 eV is 10 to the 4 Kelvin, something like 3,000 Kelvin. So 0.3 EV, a much smaller number than the 13.6 EV. So this is an important result about recombination. It's that although the key energy scale you would think should be in the problem is the ionization energy of the hydrogen, and it definitely is, recombination does not happen when the temperature reaches that energy. It happens much later because of this very large factor. Another important factor, if you look at this equation here, is that if I ask, you know, what's the free parameter as the universe expands, what does Xc depend on? The photon to baryon ratio is not a number that changes with time. And in fact, for adiabatic initial conditions from inflation, you find that it's actually uniform in space. So throughout the universe, eta is just a constant. Those are just fundamental constants. And the only thing that varies really is temperature. So the recombination history is exclusively a function of temperature. So if you know what the photon to baryon ratio is, you know the temperature at which recombination should happen. So recombination does not occur at a fixed, say, time or a fixed necessarily redshift. It occurs at a fixed temperature. Physically, temperature is what determines when that phase transition happens. Another interesting result from this Saha equation is that once you plot this curve, you can ask, you know, over what range of redshifts, since I can map redshift to temperature, or over what range of temperatures does recombination occur. And using lambda CDM, which the parameters of which can be constraints later on, you can convert this range of temperature or this range of redshift to a range of scales. And so this study actually gives you an estimate for the width of this last scattering surface or this recombination. So around redshift of 1,000 with a width of 80 or something like 20 megaparsec is the typical width of the last scattering surface, or something like 100,000 years. Okay. Any questions on this? Yes. Mm-hmm. Right, that's a really good question. And indeed, I haven't told you about this. We can get it from different ways. One is Big Bang nucleosynthesis. I don't know if you've heard about Big Bang nucleosynthesis last week or already, but yeah. Basically, Big Bang nucleosynthesis is the process by which the universe produces the light elements, so hydrogen, helium, and a few of the slightly heavier elements. And then all the heavier elements after that are produced mostly by stars and stellar explosions. But the typical abundances you get in the various elements at the end of Big Bang nucleosynthesis depends a lot on that number, a photon to baryon ratio. And the reason it does is that in the early universe you have those protons and you have those electrons. There's a moment in the history of the universe where you have free neutrons, and free neutrons have a finite lifetime. And so what happens at this stage of the universe is you have those free neutrons, and they will either convert to protons and disappear. If they all do, then the only element in the universe can be hydrogen. And so much more boring universe. None of us would be there with just hydrogen. And so you have a few minutes, that's the lifetime of those free neutrons before they turn into protons. And in those few minutes, what happens is the universe cooled fast enough to form the other elements that use neutrons and stabilize them inside of atoms. And so Big Bang nucleosynthesis is extremely sensitive to the timing at which the universe cools. And this photon to baryon number changes that timing significantly. So you can learn this number from Big Bang nucleosynthesis. Another place where you can learn it is the temperature fluctuations of the cosmic microwave background. And so that'll be lecture 2. But yeah, it's a very, very good question. Yes? Mm-hmm. Yes, that's a really good question. And so why, the question is, why should we care about the exact width of this last scattering surface? And I think you're exactly right with your answers. So first of all, when we say, if I look at the CMB, I see the universe at that moment, it's good to know that it's that moment plus or minus something. But more importantly, like you said, the width of that surface of last scattering will determine how much scattering can happen before the CMB is emitted. And that will have an impact on the diffusion damping. So we'll talk about this tomorrow. And that will also have an impact on the polarization of the CMB. And that'll be the day after. So thanks a lot. Any other questions on this? Okay. And so, right, the Saha equation, as I said, is a description of equilibrium, right? We took a reaction, and we asked, as a function of temperature, where is the equilibrium? Do I have mostly ionized or mostly neutral hydrogen? It turns out this description that just tracks how the equilibrium evolves as a function of temperature is only a good one if the rate for those reactions is very fast compared to the key rate in the universe, which is the rate of the expansion Hubble. Basically, the question is, do we have time to reach this equilibrium? If the temperature varies faster than the time it takes to reach equilibrium, we are not going to be at equilibrium at each temperature. If, on the other hand, the temperature varies very slowly, then the temperature varies a bit, the equilibrium adjusts, temperature varies a bit, the equilibrium adjusts. And so the question is, for our universe, is this a good approximation? This approximation of, always at equilibrium.
So this width of the last scattering surface is like 100 years. It does mean that there might be photons on the CMB that it's almost after recombination, right?
Mm-hmm.
So you
yes.
have only photons at the last scattering. You have photons.
Right. Yeah, so if this curve was a step function, then all the CMB photons, the question was, because there's a width to this last scattering surface, does it mean that some CMB photons are effectively emitted earlier or later? And that's exactly what it means. Because this is not a step function, some CMB photons are slightly older than others by about 100,000 years. And so the CMB photons are about 14 billion years old, plus or minus 100,000. Thanks a lot. Okay, and so this was a description of the equilibrium and how the equilibrium would change with temperature if the temperature varied very slowly. But we can actually do a bit better, and this is what the Boltzmann equation does. And so the Boltzmann equation allows you to relax the approximation or the assumption that there is equilibrium at all times, and it allows you to track the actual time dependence of the ionization fraction, taking into account how fast is the rate of those chemical reactions versus the rate of change of temperature. And so if you look at the Boltzmann equation, it looks something like this. So how much as a function of time does effectively the number of electrons change is a function of this cross-section for this reaction times this source term. And the idea here is that you're comparing effectively NE squared over H to the NE squared over NH at equilibrium. So imagine, everything evolves very slowly and we're at equilibrium at all times. The left-hand side is 0, and so I have equality here. The equality here is exactly the Saha equation we wrote before. But now what Boltzmann does is it says if there's a deviation from Saha, for example, if I have a bit too many electrons, well, then these electrons will want to combine into hydrogen, and the change of electron is going to be negative. If, on the other hand, I have too many hydrogen atoms, they will want to relax. And so this term now, minus minus, is going to be positive. And what it does is it will increase the number of electrons. So basically, this Boltzmann equation is just saying, at equilibrium, we should have this, which is the Saha equation. And if we are away from it, the system will want to relax towards it on a time scale that depends on how fast the reactions are. And in this Boltzmann equation, there's a few physical effects that happen that are important. One is that when we think about this recombination reaction, where an electron and a proton combine to form a hydrogen atom, it's not good enough to take an electron and recombine it to the ground state of the hydrogen atom directly. Because when you do, you produce a photon that has exactly that energy. And that photon will then hit another hydrogen atom and break it. So if I take an electron and a proton, I combine them into a neutral hydrogen atom, I'm happy, but it emits a photon that's going to undo this right away. So if I want to do this recombination, what I actually need to do is to break up this photon into 2 lower energy photons. And so you need to consider the fact that the hydrogen atom has several levels of energy for the electrons, and you don't want your electron to recombine directly to the ground state. So this is a lot more involved to solve in detail and include all these physical phenomena. And so the only thing I'm showing you here is the result from these Boltzmann codes that aim to just numerically solve this equation. And so here the y-axis is now in log, and the dashed line is the same Saha curve you saw before. Unfortunately, the x-axis got flipped, so now time goes from left to right. So the redshift goes down, and the temperature goes down this way. And when you compare the solution of the Boltzmann equation to the solution of Saha, you sort of see 2 differences. One is that you see a bit of a delay for recombination to occur. And you see that at late times, Saha would tell you there's no more ionization at all. There's no more free electrons at all. And the Boltzmann equation actually tells you there's a minimum abundance that freezes out. So Saha equation gives you a good order of magnitude for when recombination is, but it's not perfect because it assumes equilibrium. And that equilibrium is no longer a good approximation once the reaction rate is basically low and comparable to the expansion. And so Saha does not give a very good description of the end of recombination. Yes? Right. So yeah, the question is, what exactly is the reason why the Saha equation fails to describe recombination exactly at late times? And does it have to do with this need to break up the photon's energy into 2 to not reionize atoms? And so, broadly speaking, yes, that's the answer. On a bigger picture level, the answer is Saha assumes equilibrium at all times. So it assumes that as the temperature of the universe evolves, the universe is always at equilibrium, and the equilibrium will just follow slowly as the temperature changes. When in reality, once the temperature drops enough, this reaction of recombination and ionization becomes out of equilibrium. And why is it out of equilibrium? It is out of equilibrium because the rate of those reactions becomes too slow compared to the rate at which the temperature changes. And why is the rate slow? In part because recombination to the ground state is not effective because it produces that photons that breaks up another atom, etc. But yeah, thanks a lot for the question. That's exactly right. Okay. And so, okay, big deal. The end of recombination is a bit different. Do we care that there is, a fraction 10 to the minus 2 or 10 to the minus 3 of free electrons versus 0? Do we care about this little delay? And what I'm going to tell you next is that a key moment we care about is roughly when the ionization fraction hits 0.1. And that's because that's roughly when the photons will start to free stream. And so you can see that that's about here on this plot. And so it makes a certain difference in when you hit that temperature, and that matters for predicting the CMB properly. And so that moment, once the CMB photons start to free stream, is what we call photon decoupling. And photons decouple from the baryons when the rates of their scattering, which keeps them couples, when the rate of this scattering, the Thomson scattering, becomes slow compared to what? Compared to the one rate we have in the universe, which is the Hubble rate. That's the rate at which the temperature of things changes. So basically what you see is you're comparing the rate of this Thomson scattering, which depends on the number density of electrons, to the Hubble rate. And as the expansion proceeds, the number density of free electrons goes down, and so CMB photons see fewer and fewer electrons, so they start to interact less and less. And once you sort of reach this equality, is when photons decouples. And sorry, did I say that right? I think this should be 0.1, but I'll check, sorry. And so this decoupling, this rate happens to occur when the universe is actually significantly neutral. And I'll check this number and confirm. But basically, the CMB start to decouple from the baryons at the end of recombination, not in the middle of it. And this moment is what we call photon decoupling. On my table from the different milestones in the history of the universe was another entry that was called last scattering, when typical CMB photons might scatter off an electron for the last time. And photon decoupling and last scattering basically occur at the same time. So decoupling is when those rates are comparable. Last scattering is when the optical depth, which has to do with the probability for an electron to scatter, sort of reaches unity. And to compute the optical depth for CMB photons, say between today and last scattering, or between last scattering and today, what you need to know is, again, the rate of these reactions times how much conformal time you have. And so you can sort of see that having those two equalities at the twiddle level should happen roughly at the same time, because conformal time dimensionally is 1 over Hubble. Right. And more precisely, from this optical depth, you can derive a function that we call the visibility function. And I'll let you derive as an exercise that the visibility function is related to the optical depth in this way. And this function is the probability distribution function for a photon to last scatter at a given redshift. So what is the probability? Take a CMB photon. What is the probability for it to scatter at redshift z and never again? That's what G of z is. And so once you know the electron number density, which we've computed from the recombination history, you can compute this optical depth function, and you can compute this visibility function, and they look like this. So here's the optical depth as a function of growing redshifts. So here you sort of think of a photon going from us towards the last scattering surface, but that's a detail. And what you find is that optical depth reaches order unity around a redshift of a bit more than 1,000. And if you plot this visibility function, which again is related to the optical depth, you find this peak here. And this peak is the PDF for CMB photons to last scatter off of baryons. And so if you ask, again, when were CMB photons emitted? They were emitted around this redshift with this width. And this is the width of last scattering that you can infer from the width of recombination we talked about earlier. And so the CMB we see is roughly a snapshot of the universe at this redshift with a bit of fuzziness around it. And that's when the CMB was emitted. Any questions on this again? Yes?
So a really nice one. Is this then connected to why the CMB has a black body spectrum in certain frequencies, or is related more to the temperature?
Yes, that's a really, really good point. And so at thermal equilibrium, the universe has a certain fixed, yes. The question is this curve related to the fact that the CMB spectrum is a black body at a fixed temperature as opposed to something blurry in spectrum? And the answer is yes, exactly. So as a function of time, as the universe expands, the temperature of the universe varies. If this visibility function was very broad in redshift, then the CMB would actually be a mix of many black bodies at many different temperatures. And we might talk about this in the last lecture, what happens when you superpose two black bodies. I don't know if you know the answer to that. If I say I take a black body at temperature T1, I take all these photons, I take a black body at temperature T2, and I just put all the same photons together. What's the resulting spectrum? And naively, you might think it's a black body at T1 plus T2 over 2, you know, the average temperature. But the reality is not quite. It's this plus a spectral distortion that we call a Y distortion. And we'll talk about this. And so indeed, the fact that there's a non-zero width means that there's a non-zero level of mixing of temperatures and of, therefore, spectral distortion. But that level is very small because this is very narrow. So yeah, thanks a lot for the very good question. Any other question on this? Okay. And in order to anticipate what we'll talk about a little bit tomorrow, but mostly the day after, this is a plot of the same visibility function, but here the redshift axis went from only 100 to 5,000. If I broaden the redshift axis to include lower redshifts, and so now I'm a few thousand to actually pretty much redshift 0. So, and if the y-axis and x-axis are now log, this peak you see here is this last scattering surface we talked about a moment ago. But you might find that there's actually another peak around here. And this peak has to do with another key phase transition of the universe, which is the opposite phase transition. This is called reionization. And so here, as the universe cools down, the universe becomes neutral. But as large-scale structure forms, you form stars, and those stars will emit light that eventually can ionize the gas again. And so the early universe was ionized because it was a hot plasma. As it cooled, it became neutral. And finally, as the stars reionize it, it becomes ionized again, and scattering, Thomson scattering, can begin again. However, when the universe becomes reionized, by that point, the density has dropped a lot due to the expansion. And so the peak here is much smaller in amplitude than the original one. Nonetheless, some of the CMB photons on their way towards us, about 5 or 6% of them will actually scatter one more time before reaching us. And so for many photons, most photons, this last scattering is indeed the last scattering. For some of them, it was the penultimate scattering. And this extra scattering will actually have a lot of importance when we talk about the temperature fluctuation as well as the polarization fluctuations. Okay, the next thing I wanted to talk about, which is not directly related to the cosmic microwave background, but I think might connect with what you'll learn about the BAO, or have learned already, is this question of baryon decoupling. And so a few slides ago, we talked about how as the universe becomes neutral, towards the end of that process, the photons decouple from the baryons and start free streaming. You might think that if the photons decouple from the baryons, then the baryons also decouple from the photons. And you wouldn't be too wrong, but there's a slight difference. Yes?
How can you differentiate photons from reionization from the last scattering sources photons?
Right, great question. And the question was, when I see a CMB photon, how do I know if it's a photon that comes from the last scattering or a photon that comes from reionization? And of course, on a photon-by-photon basis, you can't tell. But when you look at the scale of the fluctuations and when you look at whether they're polarized or not, you will be able to tell for reasons that I'll explain. That's a really good question, thanks. Right, and so recombination happens towards the end of it. Photons decouple from the baryons, they start free streaming. Slightly later, baryons decouple from the photons. And so why am I making a distinction between these two? The question of decoupling, like a good definition for when a species decouples from the rest is when basically its momentum, its dynamics, is no longer affected by the rest. And the scattering, when you have scattering between photons and baryons, you have momentum exchange between photons and baryons. And of course, that exchange is symmetric. If a baryon acquires some momentum from a photon, then the photon has lost this momentum. So that seems like it should be perfectly symmetric. However, you have this exchange that's symmetric, but you should ask how much momentum was there to start with. So if the photons, for example, have more momentums to start with than the baryons, the same exchange might be negligible for the photons, but not for the baryons. And so this is actually exactly what happens. So the momentum exchange between photons and baryons in a given time is the same. It goes both ways. But the photon momentum density turns out to be a bit larger than the baryons. And that really is sort of an accident, but it has to do with the fact that as the photons and baryons dilute away differently, the momentum in one or the other may be larger or smaller. And it just turns out at this time, close to recombination, the photon momentum is a bit larger. And so the baryons will feel the pressure from the photons a bit longer than the photons will feel the baryons. And this will have an implication for the scale that's imprinted, this baryonic acoustic oscillation that you've probably heard about and we'll talk more about next time. But basically, when you look at the baryonic acoustic oscillations in the CMB and in the galaxies, the one in the CMB was imprinted just a bit earlier than in galaxies. So that's a detail, but I thought I would just mention it. Finally, to conclude, today we've talked about measuring the CMB, the average over the sky, not its fluctuations. So we've learned that it's a almost perfect black body, and we learned about this CMB temperature. So I wanted to go back and say, okay, what exactly about cosmology do we learn from just this information? And first of all, if you have a black body and you know its temperature today, the temperature that you measure, about 3 Kelvin, then you know everything there is to know about the spectrum today. So you know the energy density in radiation today. So from the CMB temperature, you know how much energy in light, in photons, is present today. And you know how much energy is present at all possible redshifts, because you know that it redshifts away with the scale factor to the 4th power. So if you measure the CMB temperature today, you know the energy density in photons in the universe at all redshifts. You don't necessarily know it at all times, because that requires converting between time and redshift, but you know it at all redshifts. And I've also told you that if you know this baryon to photon number, then you know at what temperature recombination should happen. That is a fixed temperature, about 3,000 Kelvin. And so if I know the temperature that I measure for the CMB today, and I know that it had to be emitted at 3,000 Kelvin, then I know the redshift of recombination. So I measure 3 Kelvin, I know it had to be emitted at at a temperature of 3,000 Kelvin. Therefore, I know that the universe was about 1,000 times smaller when it was emitted. So from the CMB temperature, I get the photon energy density at all redshifts, and I get the redshift of recombination or last scattering. So that's already a useful bit of information. But as we'll talk about tomorrow, there's a lot more information in the fluctuations. Okay, so going back to the stuff I'm hoping you have learned from today's lecture, an intuitive understanding of what the CMB is, this idea of expansion, therefore an early universe that's hot and ionized and in thermal equilibrium, and as the temperature cools down, the universe becomes neutral, that light is free to stream, and we get to see this black body. We've learned about this black body spectrum, the measured temperature of about 3 Kelvin, the typical frequencies of about 100 gigahertz, the typical wavelength of about millimeter, and I did not give you these numbers, but I think I'll leave it as an exercise for you to look up orders of magnitudes for those. We've talked about the Thomson scattering, which is very efficient when the universe is ionized and keeps the photons coupled to the baryons. And we've talked about the Rayleigh scattering, which occurs once the universe is neutral and is not efficient enough to keep the photons and baryons tightly coupled. We've talked about some steps in the thermal history of the universe, specifically really recombination, how the Saha equation describes the equilibrium, and how it's a really good starting point, but it's not exact. And Boltzmann equation allows you to describe the out of equilibrium recombination. And we've talked about the difference between recombination and photon decoupling or last scattering that happens just a bit after. And finally, baryon decoupling that happens yet a bit after. My understanding is I should give exercises for next time. Of course, no obligation to do all this, but if you're interested, I think these are interesting questions to look into. So again, a bit of order of magnitude estimates. Given the CMB temperature today, you know, how many CMB photons per unit volume do you expect? What are their typical energies? For example, in EV, now that you know their temperature in Kelvin, what are typical wavelengths, frequencies? Just getting to know a bit of the CMB. Another question I have for you is, I told you that the CMB was emitted soon after the Big Bang, and so the CMB is about 14 billion years old. And so one natural question is, how far from us is this last scattering surface? And I think the naive answer is, if light has propagated for 14 billion years, it should probably be 14 billion light years away. So I'd like you to think about whether that's the right answer, and if not, why. Deriving the Saha equation, a lot of resources online, including the links that I provided. Feel free to take a look. That's an instructive calculation. And perhaps a useful derivation is, given the optical depth as a function of redshift, can you show that the form of this visibility function I told you indeed represents the probability to last scatter at a given redshift? Meaning, what's the probability to scatter at that redshift and never again afterwards? And so, so feel free to think about these. Thanks a lot for your attention. I'll be happy to take more questions.
So my question is how the temperature decay with the scale factor?
Right, that's a really good question, and I probably should have started with this. So I'm assuming you've talked a bit last week about how the energy densities dilute with expansion. And so for matter, for example, you know that the energy density dilutes like the volume. So if I take a volume of the universe and I scale it up, the energy density just goes down because the volume went up. For photons, the energy density decays as the scale factor to the 4th power, which is one more power, and that's because the temperature decays as 1/A. And naively, you can think of it as the wavelength of light being like a slinky, like a spring, and that expands with the expansion. Another way you can derive it is thinking about photons that bounce inside of a box. And as you move the boxes away, as the photons bounce, there's a Doppler effect. But the real derivation is from general relativity. Thanks.
Thank you very much for the lecture. Yeah, so earlier you mentioned that after recombination, the main scattering of the photons are described by Rayleigh scattering, right? As opposed to the Thomson squared, which is more relevant pre-recombination. So my question, why is the photon decoupling time related to the inefficiency of the Thomson scattering as opposed to the Rayleigh scattering, which happens after recombination?
Can you say again? Why do they have the frequency?
Yeah, because you define the photon decoupling time as the moment which the Thomson scattering becomes inefficient with relation to the Hubble rate, right?
Right.
But, I mean, the photon decoupling happens after recombination, right? Which would imply that the main scattering would be Rayleigh's. Why we use the Thomson scattering as this definition, not the Rayleigh one?
That's a really good question. Thanks a lot for asking. And so, yes, so the Thomson scattering and the Rayleigh scattering have very different frequency scalings. So Thomson scattering doesn't care about the frequency of the photon, whereas Rayleigh scattering cares about the frequency to the 4th power. And again, that's why the sky is blue. But the idea here is that even as the Thomson scattering becomes inefficient, the Rayleigh scattering is still very, very inefficient, a lot more inefficient. But it exists, and so there are a lot of papers that have predicted the impact of this very small Rayleigh scattering on the CMB. And indeed, we expect some level of spectral distortion away from the black body due to this Rayleigh scattering. And so the way you would observe it would be to look at the CMB at the highest frequencies, because that's where Rayleigh scattering is more important. But even there, it's a very, very small effects, and it's very far from being detectable with current experiments. But yeah, really good question.
Thank you very much.
Thanks.
So if I didn't better understand, you said that the
BAOs measured from the CMB are different than the BAOs measured from the large-scale structure, right?
Very slightly, yeah.
Yeah. So, can you explain again why? Why is that?
Right, and I'll talk a lot more about it tomorrow, but I think it's good for me to front load as much as I can because there's so much to cover tomorrow. So thanks for the question. One way to think about the baryonic acoustic oscillation scale, what that scale is it is how far can a sound wave propagate between the Big Bang and the moment you're looking at it. And in the CMB, the moment you're looking at it is the photon decoupling or the glass scattering. In the large-scale structure, it is this baryon decoupling. Sometimes you'll hear this moment called the end of the drag era. But basically what happens is that between the photon decoupling and the baryon decoupling, there's a little bit of time. And in that time, sound waves can propagate a little bit further. And so the BO scales that you'll see in the large-scale structure is a tiny little bit larger than in the CMB. It's really not a large effect. I mostly just wanted to mention in case you see those two things and wonder why they're different. Yeah.
So maybe you mentioned it and I missed it, but is there a way to analytically derive, for example, the black body spectrum from the CMB photons directly?
And what do you mean by derive?
I will hope that it will come from something like the visibility function, and then from that you can estimate the shape at least of the black body spectrum or something like that.
Yeah. So that's a really good point, and I think there's also a more general question: is how does a photon system relax towards black body?
Right. Yes.
And is this happening in the universe? And again, this Boltzmann equation is a way to answer this question. So you have this Boltzmann equation that describes how CMB photons, or photons in general, interact with their environments. And that interaction will typically do two things. One is it will redistribute the energies between the photons. And the other one is it may create or destroy photons. And for black body, you sort of need both things to happen. For black body, you may know that the chemical potential of photons is 0, or in other words, that the number of photons is determined. So if I have to take a box and you tell me there's a black body at this temperature, I know exactly how many photons there are. And so for that to happen, you need the processes that, you need two sorts of processes to be efficient. One is the ones that will redistribute energy among photons, and two is the ones that create or destroy photons. And in fact, in the history of the universe, there's a moment when one or both of these processes stop being efficient. There's actually a key redshift, about 10 to the 6. So not redshift of 1,000 when the CMB is emitted, redshift of 1,000,000. That's called the black body photosphere of the universe. And the reason it's called that is because at earlier times than this, the universe is dense enough that if anyone were to dump energies into photons or create some photons, the system would be able to redistribute that energy and readjust the number of photons and re-relax to a black body.
Right.
And after redshift of 1,000,000, you lose the ability to effectively create and destroy photons. And so when that happens, you create a spectral distortion to the CMB, to black body. It's called a mu distortion. And later on, you create a different one that's called a Y. I'm hoping to talk a bit about this on Friday. But basically, yeah, you can very precisely show when and why you would have a black body, what processes maintain it a black body actively, and things like this. So,
right.
Yeah.
Thank you.
No, yeah.
Going once, going twice. Okay, let's thank
Thank you.
Emmanuel again.
And yeah, thank you for the very good questions. Cool.